welcome to AIM 307, High Performance and Cost-Effective Model Deployment with Amazon SageMaker. I am Alan. I'm a Senior Product Manager with Amazon SageMaker. I've been with AWS for about 4 years, and before that, I've been working on other cloud technologies in the big data space. With me here today is Raghu. He'll be presenting the second half of this, and he'll introduce himself a bit later. If you find that my voice is too loud or too quiet, there is a volume knob on the right side of your headphones, and you toggle that up and down. And because this is a silent session, we'll be taking questions just outside the door when we finish. So be sure to note any questions you have. We'll be hanging out there right after the session. So as part of the session today, we'll be covering 2 main topics, followed by a demo. The first topic is how do you choose the best inference option with Amazon SageMaker? So as part of this topic, we'll be going over an introduction of what options we offer on SageMaker for model deployment, give an overview of the different inference options, and then go through a simple guide and flowchart for choosing the best inference option. Following that, we'll also then go over cost optimization techniques for SageMaker deployments, by introducing topics such as SageMaker savings plans, how do you improve utilization on these instances, and picking the right instance to start with, followed by an introduction to auto-scaling and how do you optimize models, because optimized models use less resources, which then result in cost optimization. And finally, we'll do a demo of some of these topics we've covered. So let's get started. So with Amazon SageMaker, it offers a wide variety of features and infrastructure to help you meet your workload needs. So first is we have over 70 plus instances with varying levels of compute and memory to meet your use cases, including accelerated instances using GPUs and also instances that are designed specifically for ML workloads, such as our Inference instances. With so many instances, it could be hard to find which instance works the best and how many you should use. So we have a fully managed service called Inference Recommender to help you provide automatic deployment recommendations. And you can also use it as a fully managed load testing tool. We have a wide set of deployment options from real-time, asynchronous, batch, and serverless endpoints. This is one of the main topics we'll be covering today. So I'll be covering that over the next few slides. For some of these options, we also have fully managed deployment strategies, such as canary or linear traffic shifting models to help you safely roll out new versions of your model, and then automatically roll back if there are any issues. We also offer a set of features to help you make cost-effective deployments. This is the second topic we'll be covering today. So we'll go over these in a lot more detail. For example, we have features that let you put multiple models or containers onto the same instance. We have a serverless offering, and we also support auto-scaling. And finally, we have built-in integration with multiple ML ops services within SageMaker to help you productionize and automate your ML workflows, such as using Model Monitor to monitor for drift and alert you if there are any, and implement full CI/CD ML pipelines using SageMaker pipelines. And you can also register models to create a catalog of your ML models using SageMaker Model Registry. So broadly speaking, SageMaker model deployment has 4 options: real-time inference, serverless inference, asynchronous inference, and batch inference. We can broadly split this into 2 categories: online inference and batch inference. With online inference, your application expects an inference to come back with every request that it makes. And SageMaker offers real-time, serverless, and asynchronous for this use case. And we also have a batch use case where your application runs inference on a set of data all at once, and your application perhaps uses the results of that batch inference. So we also have the similarly named batch inference for this use case. Let's take a look at this in more depth, right? So first, we have real-time inference. This is a synchronous inference option. So your application makes the request. It waits for the inference to come back before it moves forward. It is instance-based, so you have to pick and choose the instance that works best for you, or use Inference Recommender to find which instance works the best. Because there's always an instance up and running, it is low latency because it's always ready to serve your inference for the request. It's good for when you have payloads that are less than 6 megabytes, or when you need a request timeout or runtime of less than 60 seconds. Because there's always an instance up and running, we also provide features to help you optimize costs and improve utilization of these instances by allowing you to deploy multiple models and containers onto a single instance. We also provide features to help you flight changes using A/B testing so you can see which version works the best. And we also have features to incrementally switch traffic so you can detect issues early and automatically roll back with our blue, green, or canary deployments. With real-time inference, you can also get an automatic capture of the inputs and outputs coming in and out of your model. And you can use this later for auditing or for retraining purposes. Some example use cases we have for real-time inference are ad serving, personalized recommendations, and fraud detection. The common pattern between these is that you really need inference response really fast. For example, with fraud detection, if there are any suspicious activity, you want that to be detected immediately so that your application doesn't go ahead with fraudulent activity. Next, we have serverless inference. This actually went GA just earlier today. And similar to real-time inference, it is a synchronous inference option. But in this case, you don't need to pick any instances. You just need to tell us how much memory you need access to. And because there are no instances, you only pay for the duration of your inference requests. This means, when your model isn't, or your endpoint isn't serving any traffic, there's no cost for you. We'll automatically scale up and down in response to the traffic that your endpoint is seeing. So it's really cost-effective for your workloads that are intermittent or have unpredictable traffic, or when you have periods of no traffic, but you still need something available. And when we scale, the first few requests will see a higher latency. So it's good for workloads that can tolerate this increase in latency while we scale up. It's similarly good for workloads that with payload size of less than 4 megabytes and request durations of less than 60 seconds. It has a very similar deployment configuration to real-time inference. So if your workload changes, you can easily switch between real-time and serverless inference. And the invoke pattern is exactly the same between them. So if you switch, your application likely does not have to make any updates. Some example use cases for serverless inference is analyzing data from documents, processing forms, and chatbots. The common theme between these is that during the day, you may see fluctuations in your customers that are using these applications or these use cases, so it can be unpredictable. For example, in the case of chatbots, when you release something new, you may see a lot of questions from customers asking about certain things, so you may get an influx in traffic there, or maybe after midnight, most of your customers are sleeping, so you don't get too much traffic, maybe just 1 or 2 requests per hour. So in these cases, serverless is really good because it'll automatically scale up and down to meet those requirements, and you don't pay for when your endpoint isn't seeing any requests. Next, we have asynchronous inference. As named, this model is asynchronous, so your application can make an inference request. It can go ahead and do something else and then check back on the result of that inference later. It is also instance-based, so you can pick and choose the instance that works best for that workload. And it is really good for large payloads up to 1 gigabyte and of unstructured data, such as images, videos, text. And it's really good for when you have processing times that are in the magnitude of minutes, up to 15 minutes right now. The main difference with asynchronous inference is that there is a built-in queue for the requests. So as your application makes requests to this endpoint, it will automatically queue those. And this will actually act as a buffer for the instance that you pick. So then the instance will just simply pick up requests from the queue. As it finishes requests, So the main thing to keep in mind here for asynchronous inference is that you just need to pick instances and your auto-scaling policy based on your desired queue drain rate. So how fast you want inference requests back for the requests that are in the queue. You can scale down to 0 to optimize for cost. So if you're not seeing any requests, you can scale down to 0 and you won't be charged for that endpoint. And we also have features similar to real-time inference to help you safely deploy changes with blue, green, or canary deployments. Some example use cases are image synthesis, extracting known entities from documents, and anomaly detection for time series data. So the common theme across these is that you can fire off one of these requests and come back and check on these later. For example, with anomaly detection, you may have thousands of sensors that are sending data into your endpoint, and these thousands of requests will just automatically be queued, and the instance behind it will pick up those requests and process them. So maybe you just need to optimize and pick the instance that you need for perhaps maybe like a queue drain rate of 10 minutes. You just want everything to be processed within 10 minutes. So that's the main difference with asynchronous inference. And finally, we have batch inference. This is our offline inference option. All the input data is in S3, and it also outputs to S3. So it's the highest throughput inference option because it happens in batches. It's good for applications that don't necessarily need to make a request to get the inference. It can wait for all of the results to come back before processing or going ahead. It is instance-based, so you pick and choose the instance that works best for your model. It's really good for processing gigabytes of data for all data types and with a processing time in the magnitude of days. So really large payloads, really large workloads are possible with batch inference. It has built-in features to help you split, filter, and join structured data. And if you're using structured data with batch inference, we'll also automatically distribute the processing for high performance. And because it is a batch inference job, you only pay for the duration of that job as well. Some example use cases are propensity modeling, predictive maintenance, and churn prediction. The common theme across these is that you don't necessarily need to react to a specific request. All of these can happen on a schedule or on demand. For example, with churn prediction, you may have a set of customers that you want to see what the likelihood is that they will churn, and then have someone follow up with them throughout the day or the week, right? So you can run these on a daily or weekly basis. Now we've gone over the different inference options we have. Here's a simple flow chart to help you pick which ones you should start with. And this is not like a very strict flow chart, so if you find that other options work best for you, feel free to use those options. This is really just a way to help you get to a starting point. So we can walk through this flowchart together, starting from the top left there. Does your workload need to return an inference for each request to your model? So this basically tries to segment whether or not you need an online inference option or a batch inference option. So if your workload or application can wait until all the requests are processed and then just use the inference results, batch is a good place to start because it has the most permissive of the payload size limits and the runtime limits because it's in gigabytes and on the magnitude of days. But if you do need a response for every single request immediately, then one of our online options would be a good starting point. So then would it be helpful to queue requests due to longer processing times or larger payloads? If so, then async is a good place to start. For example, if you need longer processing time because you're doing image recognition, because you have a form submission process and you want ML to automatically analyze those forms, then async is a good place to start because it supports payload sizes up to 1 gigabyte with runtimes in the order of 15 minutes. But if you need something real time instead of asynchronous or synchronous, then we need to move on to our serverless or real-time options. Now, does your workload have intermittent traffic patterns or periods of no traffic? If it does, then serverless is a good place to start because it'll scale up and down to meet those needs, and you don't pay for idle. Now, if your workload has sustained traffic or you need very low and consistent latency throughout the request, then real-time inference is the place to start because it always has an instance up and running. So it's always ready to serve your request. There's no latency to scale, there's no latency to wait for the endpoint to scale. Now we went over the different inference options, how you programmatically call SageMaker and put that into your application or automate some of this for CI/CD. So the first is we have the AWS command line interface option. This is good for if you're trying to build a script. This is a common command line interface set for most AWS services. So when you get it, you also see commands for other services. So you can use the command line interface for building scripts. Alternatively, you could call our REST APIs directly. If you're trying to programmatically set up SageMaker, we also offer different infrastructure as code options, such as CloudFormation and the AWS Cloud Development Kit. Now, if you're trying to call SageMaker through an SDK interface, we have the AWS SDK and the SageMaker Python SDK. So the SageMaker Python SDK is unique to SageMaker. Let's take a look at what the differences are between these two. So the first is the AWS SDK. This is a set of pretty granular low-level APIs. You can think of them as SDK alternatives to the REST APIs that we offer. It's offered in multiple languages, Java, C++, Python, for example. And this single SDK contains APIs for multiple AWS services. And it's really targeted for any engineer, from DevOps engineers to ML engineers. And because it is quite low level, you'll see that number of API calls you have to make is quite high. But also at the same time, then you know exactly what's happening behind the scenes because you're making those API calls yourself. And because it is a common set of SDK, you'll see that it's pre-installed on managed compute services like AWS Lambda. Now we can take a look at the SageMaker Python SDK. This set is a bit higher level. We actually wrap multiple AWS SDK calls into one just to make it easier to use. It's only available in the Python language for the Amazon SageMaker services. And it's really intended for data scientists, and it's in terms of size, it's slightly bigger. But the trade-off is that it's easier to use, you get simpler request and response schemas, and you just write less code in general. So what I recommend is you start with the Python SDK, the SageMaker Python SDK, and if needed, you can also bring in the AWS SDK for things that aren't supported in the SageMaker SDK. So we went over the different deployment options we have in SageMaker, presented a flowchart of how do you pick a good starting point. I'll bring on my co-presenter, Raghu, to introduce himself and also walk you through the different cost optimization options we have, and followed by a demo.
Hey everyone, thanks Alan for giving us an overview of all the deployment options we have. This is Raghu Ramesha. I'm a machine learning solutions architect with AWS SageMaker team. I help customers build, deploy, and optimize models on SageMaker. So now that we've looked at different deployment options, let's take a closer look at how we can optimize cost for each deployment option. So broadly speaking, it can be divided into two different categories. One, buying yourself a SageMaker savings plan. We'll talk more about this on the next slide. Second, as you can see, you can optimize your cost across various inference options. So the first one to start off with is real-time inference. For real-time inference, you can enable auto scaling. That is to bring in only instances only when you have to serve traffic, and bring down the number of instances when you do not have traffic. Second, you can enable, since real-time inferences are always on, you can enable, you can use multiple containers and models to pack that endpoint to best utilize that endpoint. Second, with batch, again, it's an instance-based deployment option, but you can use the appropriate number of workers and have a concurrent mechanism to optimize the batch job to complete faster. With async inference, we offer a unique capability to scale down the number of instances to 0. So with this, When you have intermittent traffic coming in, you can scale down the instance to 0 when you do not see any traffic and scale up the instances when you see traffic. This way you would save costs when you do not have any incoming traffic that's coming in. With serverless, you can optimize your cost and update your performance and increase your performance by choosing the right memory size. And we'll talk more about this on the next demo. As you can see, a common pattern across multiple inference options is to choose the right instance type. That's why we provide a managed service called as SageMaker Inference Recommender, which helps you pick the right instance, the instance count, the model configurations, and the container configurations to help you save costs and optimize your performance. Coming back, so we talked briefly about the savings plan. Savings plan is a flexible pricing model that helps customers like you save 64% of the cost by opting to be on this plan by making a small commitment of consistent usage for a 1-year or a 3-year plan. So by choosing a SageMaker savings plan, any instances that you spin up can automatically are eligible for using the SageMaker savings plan, and it can be extended to studio notebooks, data wrangler, training, and for inference in specific, you can use it for real-time inference and batch inference. Again, with advantage of using savings plan is when you have consistent usage, any usage until the savings plan amount is charged at that rate, and anything beyond that is an on-demand rate. Next, now that we've seen the different inference options, let's pick a real-time inference, since this is the most costliest of sorts, where you have to have inference all the time. Let's see how we can optimize cost for real-time inference. So broadly speaking, there are 3 ways you can optimize performance for real-time inference. One, by using MME or the multi-model endpoints. With a multi-model endpoints, you can pack up to thousands of models onto the same endpoint. And usually these work best when you have similar models in terms of size and framework. And also, one of the points to note is when you do not have to call one model continuously, when you can call one model and another model later, let's say X and Y, you can use these use cases work best for multi-model endpoints. And whenever you call a model, these models are dynamically loaded into memory, and your request is served. The second time you call the model, since the model is already saved in your memory, the latency of response for the model will be lesser. Again, note that when you do not have models in memory, there could be a cold start time. So we recommend you use multi-model endpoints when you do not have any strict latency requirements for a single model. Secondly, we have multi-container endpoints or MCEs. So with MCE, you can chain up to 15 different containers of different various frameworks. Let's say you have XGBoost, XGBoost, scikit-learn, any different frameworks. And the best part about using a multi-container endpoint is you have all the models and the containers are loaded in memory, unlike your multi-model endpoints. And it works best when you have different, when the containers exhibit same usage and performance characteristics. And also one advantage of using a multi-container endpoint is you can invoke each container individually, unlike the other options. And the third option is serial inference pipeline. Serial inference pipeline is an offering where we allow you to chain multiple containers, form a pipeline of sorts, where you can have logic to, let's say, do some pre-processing and then model deployment, and you can chain those steps together. And since all these containers are hosted on the same EC2 instance, your latency is going to be really, really low. Note that these pipelines are immutable. If you need to modify them, you need to create another pipeline. We spoke briefly about Inference Recommender, which was a service we launched at reInvent 2021. So with Inference Recommender, the goal is to allow customers to take their models into production faster by automating their load testing and model tuning process. So with Inference Recommender, if you have models on model registry, you can directly invoke them and configure your load testing job and model tuning parameters like container configurations and environment variables of sorts to basically run your load test. It saves customers a lot of time and effort, right? So basically, there are two types of Inference Recommender jobs. One, the default job, which provides you preliminary recommendations. And for instance, you have the instance count, instance type, endpoint configuration details like model latency, the number of invocations that you set, and things like that, and cost as well. With the advanced job, you can run customized load testing. When I mean customized load testing, if you have a production scenario which needs to run for, like, say, more than an hour or 2 hours, and you have a certain traffic pattern of user spawning processes, you can basically mimic that using an advanced Inference Recommender job. And towards the end, stick on to see how we show a demo of Inference Recommender with both the types of job. Also, basically you can get lot of details. These are emitted into CloudWatch, so you can read from them and process them as well. A very important aspect of any inference option is auto scaling, right? So auto scaling is an out-of-the-box feature that helps customers save costs by only having the appropriate amount of instances to serve their traffic, also having high availability. So for high availability, when we advise customers to use multiple instances to deploy on production, the reason being, SageMaker automatically distributes the instances across multiple AZs. And if you have your endpoint configured on a VPC, we advise to provide at least 2 subnets and different AZs so that SageMaker can distribute the instances across the different AZs. Also, one point to note is with auto scaling, there is no traffic interruption when instances are being added or removed. There are 2 basic types of auto scaling. One, simple or target tracking scaling, which is where you have a CloudWatch metric and a threshold that you create. So any breach of the threshold will start the auto scaling policy and scale accordingly to increase or decrease the number of instances. The second type of auto scaling is your advanced scaling. So in your advanced auto scaling, you have again 3 types. So one is step scaling, where this is a more aggressive kind of scaling, where if there is a breach or alarm, you increase by X number of instances or X amount of size instead of, let's say, auto scaling doing it by 1 or 2, right? So these are used for only when you want to dynamically scale the number of instances. So second type is called schedule scaling. This schedule scaling is used when you know your traffic is going to follow a certain pattern in a day, week, or a month, right? So you can have a cron-like job, a cron-like schedule to automatically bring in instances on a Monday morning per se when you have most traffic, and scale down on a Friday evening when you do not have much traffic. So also for auto scaling, the general metric that we allow you that we encourage you to use are like say CPU, average CPU utilization, or maximum number of invocations. But we also allow customers to choose their own custom CloudWatch metric to scale against as well. Also, auto scaling, we'll take a look at auto scaling in the demo as well. But one important thing to note is auto scaling also allows you to have custom scale in and scale out times. What I mean by custom scale in and scale out times is how often do you want the auto scaling job to start, and how often do you want to add more instances. You can specify the amount of time in seconds. And how often do you want the job to go down when there is an alarm breach? You can configure that as well. So now that we've looked at different options to see how we can optimize the cost for model deployment, another very important aspect of it is to actually optimize the models itself. With optimization of models, it helps you basically reduce the time and also save costs, and you can do more on a same instance rather than running it on a beefy large instance. So for optimization of models, we like generally when you have deep learning models, 90% of the cost is spent on inference rather than training, and these are basically due to two reasons. One being your standalone GPU instances. With standalone GPU instances, these are typically made for training or distributed training per se, and they're not optimized for inference, right? For the reason is with optimized inference options like Triton or even Inferentia, you can optimize these models and use your instance better than how it's usually found, right? So also we introduced a service called SageMaker Neo, which helps you compile and optimize models on SageMaker, and we've seen that this does so by reducing the memory imprint of the model on that particular instance. And we have a very interesting scenario here. This one we used in SageMaker Neo to optimize the model, and we saw this is a ResNet image classification model. As you can see, with Neo and without Neo, we were able to bring down the inference cost and also optimize the model for better performance. Let's say for a G4DN instance, it was able to do more on a G4DL instance. Let's say increase the number of models you could deploy on an instance rather than using one model per se, right? So we also encourage you to check NVIDIA Triton, which is a great service offering which we host on SageMaker as well, and AWS Inferentia, which allows you to run on instances which has higher capabilities as well. Perfect. This brings an end to our presentation, but let's move to the more interesting part, which is our demo. In our demo, we've spoken a lot about the different inference options and how we can optimize, right? So in the demo, I'm going to be showing you three different inference options. One your async inference, second your serverless inference, and thirdly your inference recommender. And we'll show how to configure your auto scaling and how we can configure bringing down to 0 with async. And also with your inference recommender, we'll show you how to run your basic and also your advanced job. Okay, excellent. Okay, first we'll start off with our async inference. So asynchronous inference is used when you have intermittent traffic. You don't want to pay for the instances when you do not have incoming traffic or incoming workloads, right? So that's where we'll show you how you can configure the instance count to 0 when you do not have any traffic. So here, I am actually using SageMaker Boto 3 SDK, but you can do it as Alan mentioned before, you can do it with Python SDK as well. So we're going to skip through most of the setup part, but here to just talk briefly, which is going to be common across multiple demos, is going to be how you set up your SageMaker Boto 3 sessions and what region you are going to use and what runtime are you going to use. So here we set that up in this particular cell. And also to run your synchronous inference, we only need, you can have SageMaker full access policy enabled. And if you have to send any SNS notifications, we encourage you to have this particular SNS policy they added to your IAM role. Here, we're going to be working with an XGBoost pre-trained XGBoost model. So basically, inference can be divided into 3 different steps. One, you create your model. Either you bring your own model that is trained elsewhere or locally. Second, you create an endpoint configuration, which is where you configure what kind of endpoint and what kind of instances that you want to use. And third, you create an endpoint. And lastly, you'll serve traffic to that endpoint. So here, I have a pre-trained XGBoost model that I'm using that is stored on an S3 bucket that I download. Next, I create this model, and like I said, I move that model to an S3 bucket, and all we need to do is SageMaker provides a way for these models to be in a certain format, that is in a model.tar.gz. As long as your model is in that particular format, you can host it on SageMaker. Now that we have the model here, we'll specify using an XGBoost image as our primary container. We'll fetch that XGBoost image here, and we'll using that as a model URL that we have stored the model in. We'll go ahead and create this model. This model is created on SageMaker right now. So it says, okay, now that we've created this model, what's the next step? The next step is actually going to create your endpoint configuration. With your endpoint configuration, one thing to note is there are a couple of important aspects to note in this particular async configuration. As you can see, the endpoint configuration has a particular name. We say endpoint config name. We are going to say what model are we going to use, what is the instance count that we are going to use, and what is the first initial instance count that we set up with, right? And then we can attach an auto-scaling policy on that particular endpoint. Now that we've set up our endpoint configuration with the type of instances that we're going to run, we'll see how we can configure the async inference config in particular. So for async inference config, we'll say where we are going to put our output to, that is our S3 path. And also an important configuration is your client config. So the maximum invocations per instance is the maximum number of concurrent requests that is sent by the SageMaker client to the model container. If there is no value provided, SageMaker chooses an optimal value for you. So this is a unique characteristic that we need to specify in our async inference config. Next that we've created this config, and the config has this particular config name, we'll go ahead and create an endpoint with it, which is our third step, right? So if you see here, we say create endpoint using this particular config, and what is my endpoint name. Now we trigger that off, and we wait for the endpoint to create. It's in waiting state, and then after a while, a couple of minutes, it's in service, and it's active to serve requests to your customers. Next, a very important aspect that we spoke about earlier was to set up your auto scaling. With your auto scaling policy, you say that if there is we register a scalable target, that is what is going to be our desired instance count, meaning like I said before, there's an important configuration here where we specify the minimum capacity of instances at any point in time where there is no traffic is going to be 0, and the maximum number of instances that are going to be used to serve my traffic is 5. And how do I determine when to start my auto scaling? That is used by using our target tracking policy. As we spoke before, there was 2 types of auto scaling policy: simple or target tracking, and advanced. In this case, we are using a simple or a target tracking policy here. And what is the metric that we are going to use? There is a CloudWatch metric that we use here, that is the approximate backlog size per instance. And we say if the average approximate backlog size per instance is greater than 5 or any particular value for that, start your auto scaling activity. If the value drops below a threshold, that is where your auto scaling activity will again start to scale down the number of instances. Another important configuration parameter is your scale in and scale out time. Your scale out time is how often you want to scale out the number of instances. You can either have it, you can follow a conservative approach to scale out gradually, or you can have an aggressive approach to scale out more often. So in this case, it's 300 seconds is what is set for scaling out activity. And scale in is how often do we want the scale in number of instances to come down. So this is to note that even if you set a higher scale in time, if we note that if there is, we want to maintain high availability of your application, that's where we use due diligence to make sure your application is always available to serve your customers across AZs. So we'll use that as a metric. Now that we've created the endpoint and attached the auto scaling policy to it, let's go ahead and invoke that endpoint. To invoke that endpoint, I have some files that are stored in S3. In this case, it's an XGBoost container, and I have some libsvm files that I make invoke against. And we do an invoke endpoint, and this is the API that we use. We say the only inputs we need is the endpoint name and where our input resides. That is our S3 bucket, or it could be your local path as well. Now, everything else kind of remains the same, where we go look at the output location. We'll see if there are any errors in this particular stage. Now that we've seen, which waits for the output when you do an invoke endpoint, and I see that output is generated, right? So actually, async endpoints are not used to make one single request, right? Like we saw before, there's a managed queue that is present when you want to make multiple invocations. That's what we're going to do here next. So in this one, I'm going to send 25 different requests. Or this, you can basically bump up this number to your desired instance, desired invoke pattern, and you can test it as well. And you can see this is invoking an endpoint with a certain file, and this is using a certain file, and we get the output of that as well, right? So with multiple invokes, it was able to achieve that, the response in a particular set of time as well. If you look closely, let's see how our auto scaling policy helped achieve us this latency as well. So if you look closely on this particular image that we have here, the metric that we use is backlog size per instance, right? So if the backlog size is growing, and this backlog size is generally growing when you have multiple invoke requests coming in, and it is stored on your buffer or your queue, right? When there is a high amount of request that comes in, the number of instances gradually increases. When the number of instances gradually increases, that's where your backlog also decreases. That's where you see the decrease in the graph, and there is a complete dip. This is when you do not have any instances or any invocation requests that are in the queue and all have been served. So right now, as you can see, the instance count that I had set was in between. Initial instance count was 1, and it can scale between 0 to 5. So initially, at the peak traffic, that is probably here, is where we see that the instance count is 5, which is reached the maximum. And also, when all the requests in the backlog have been served, the instance count was reduced, and now you can see that the current instance count is 0. So what happens after this is, if you have any requests coming in, or if you do not have any requests, you do not have to pay for it. Only when you have new requests coming in, the auto scaling policy, if the threshold is exceeded, and that's when your number of instances will be increased, and that's when only you will be charged. So next one is just we deregister our auto scaling policy and delete the endpoint. So we have 2 more demos. Another interesting deployment option is what we released when GA yesterday, which is called the SageMaker serverless inference option. With serverless inference option, I'll show you how we can configure it and how also you can compare it against your real-time endpoint, like how we configured before, right? So for using this, again, I'm using the Boto 3 SDK, but we have the Python SDK support as well. So the setup kind of remains the same, where we set up our SageMaker session, and what is the instance that we want to choose. In the previous demo, we saw that we did not train the model on SageMaker. We just got it as a model.tar.gz on an S3 bucket. But in this case, I'm going to show you how we can train it and also deploy it. So we use the estimator to train the model, and we choose what is the kind of instance that we want to choose, that we want to pick for training. First, we retrieve the data from an S3 bucket, which is what we're using is an abalone data set. Next, we copy the data, the training data set onto a S3 bucket. Next, we basically set out the model training layout. In this, basically what we do is we pick the container, like the primary container that we want to use for our model training, and that is our XGBoost container. We can do so by using an image retrieve URI. In this case, I'm using a SageMaker one first party container, which is what we provide. And this is where we create an estimator. Estimator is nothing but it's a job which helps you which kicks off by using your container, and your model is trained on that particular container. Next, we can set some hyperparameters that are used for training your job, and how many epochs and a lot of other parameters that we can set here. Next, when we call the fit function, that is when your training starts. And you can see here it's looking at our model, and it's going to train. And it says, okay, now your model is trained. Let's go pick it up from our S3 bucket. So one way to do that is by using a model data function of an estimator. So in this, we use the model data to retrieve the model that was that the output of a training job, and we store it onto S3 bucket. This is again starting from the first step, what we saw it in asynchronous inference. Now we are on the since we are on the same page. Now the first step was to actually create the model. Now that we have the model trained, let's go ahead and create that model in SageMaker. So in SageMaker, we use the API called as create model API. Again, we're using a BYOC container instead of our 1P container. This is just to show the different aspects that you could use and flexibility of picking containers to deploy your model. In this case, I create the model using a BYOC container. The next thing is the second step again remains the same, creating your endpoint config. But one thing to note here is for serverless, as the name goes, you do not have to manage any instances. That's where in your serverless configuration, which is as part of your endpoint config, we have only two parameters that you have to specify. One is your memory size in MB. We support up to 1 to 6 GB. The memory size of your endpoint is basically how big your memory of that endpoint has to be. It need not be any instance wise. Like and a general practice that we recommend using is if your model is, let's say, 4 GB, we specify you to use anything between 4 to 6 GB for the memory of that particular endpoint, serverless endpoint. And the second parameter that we specify is our maximum concurrency. So the maximum concurrency is the maximum number of concurrent invocations that your endpoint can process. At this point, it can be anywhere between 1 to 50 concurrent requests that your endpoint can take as well. Just to compare how the configuration is going to look different for rather than a real-time endpoint than a serverless endpoint is, what's taken off from you is like the load off from you is you don't need to specify the instance type that you want to deploy on, nor the instance count. As you can see here, when I'm this is just a commented code to show you what it would take to create a real-time endpoint versus a serverless endpoint. In this case, I have to specify the type and count of that instance and also create that endpoint config, which is not required on your serverless inference. It's taken care by us for you. Next, the third point is now we've created an endpoint config. Let's go ahead and create an endpoint itself. Now we use the create endpoint API to create that particular endpoint for you, and it's waiting and now it's in service. Let's go ahead and describe that endpoint. As you can see from this particular one, you can see the configuration that you provided. That's your memory size and your maximum concurrency. And when we invoke that endpoint, we have spun up the instance that is appropriate for you, and your response comes to you at the lowest possible latency is possible, right? And the last but not the least is where we go ahead and delete that particular endpoint after what we have done. So again, to note, there could be some cold start times depending on the spin up of that at particular endpoint. Also, it depends on your model size as well. The last demo that we have is the most exciting one, where we launched on the last reInvent, and we've spoken a lot of cost optimization, was to use the right instance type. That's one of the reasons we launched this managed capability called SageMaker Inference Recommender, which I typically have seen customers save a lot of time and effort to pick the right instance and the configurations. So for using Inference Recommender, you basically set up everything remains the same across the 3 notebooks. We create the SageMaker sessions. One of the requirements for using an Inference Recommender is you might have created your model elsewhere, like any other solution that we proposed. As long as you have it in the model registry, which is what we use for versioning models in production, you can use Inference Recommender. So to understand more about the model, you can provide as much or as little as metadata as possible. When I mean metadata, it could be what ML framework your model is using. Let's say it can be TensorFlow model, PyTorch, or XGBoost, or what is the ML domain of your problem. It could be your computer vision, NLP, or just machine learning. It just helps us get ahead and pick the right kind of instances for featuring the right problem type. The last but not the least is what we specify the task. Is it a classification task? Is it a regression task or an object detection? You can specify as much as possible or as little as possible. Now that we have the different layouts set up, let's go ahead and get the model. In this case, again, I'm training a ResNet 50 model here. So we have the model. The thing to note is how we upload it onto S3 bucket and also have it as part of your model registry. Now that we have the model trained and in a tarball format, another aspect what we need is to make an inference. You need a payload against what you need to make an inference. So we basically read, let's say your payload is a CSV file. So that is zipped into a format as a payload.tar.gz, which we use to make that inference to your endpoint. So, so there are 2 things required. One, your model.tar.gz. Second, your payload.tar.gz. We upload the payload.tar.gz into the S3 bucket. Next, like I said, you register your model onto the model registry. For that, we create, there are 2 steps here. One, we create a model group. The reason we create a model group is if you, let's say you have 2 models that you want to test against in your production, right? So you can create multiple models onto this model group and register into your model registry. Tomorrow, you have a model that is trained again. You can version that model and update it onto the model registry, and you can pick the right version of your model to deploy it on production. Now that we've created the model group here, we use the create model package group function to create that model package group, and we specify where our model was located and all the different parameters that we mentioned, like the domain, task, we mentioned that here, and we register onto the model registry. Now that we've registered onto the model registry, there's an optional step, as we showed on the last slide, was model optimization. Here you could basically use Neo to optimize your model. In this case, I'm using Neo to optimize our model. And the input is going to be just your model and the type of configuration it kind of requires. So once our model has come back from Neo, is a more optimized and the cost-effective model, let's go ahead. We've specified the different task and the model package group. If we describe the model package group here, which is describe function, you'll see that was listed here. Let's say the domain I chose was a computer vision. Like I mentioned, it was a ResNet 50 model, and the domain it belongs to is computer vision, and the task was image classification. And also this ties down to the last example, that the last slide we showed before was how we optimized the model with Neo for a ResNet image classification model. This is the same exact model that we used. And we were able to achieve almost twice the speed by lowering your cost as well. Now that we have the model, let's get to the most interesting part where we run the instance recommender job. There are two kinds of job you can run. One, your default job, and your advanced job or custom job. Uh, in this, I'll show you both. First, let's start with the default job. So with the default job, all your input configuration requires is your model package ARN, which we just created, and we specify the job type as to be default. You need not pick any particular instance that you want to do recommendations against. We do that for you using your metadata or based on our previous runs. Let's look at the result of running this job. The default job usually comes back within an hour, and you're only charged for instances that are spun up during that time. So you do not have to worry about maybe shutting down your instance after the use. So we take care of that for you. So if you look closely against the recommendation results of your default job, it has your model latency, your maximum number of invocations that we did, and what was the cost per hour, and also what is the cost per instance. Depending on the results that you get, you can choose the appropriate instance. And let's look at, for this particular job, what was the result. So if you detail out the result, and you can visualize this on Studio as well, which I'll show you in a bit. We see that there is this is the kind of instances that we checked against. It was a compute instance, C5 instance, and an M5 instance, and the cost was per instance was X, and what was the number of invocations and the latency. So looking at this, if you want a lower latency, I would choose to host a lower latency of 1026 seconds. You could use a C5 instance. If you can tolerate a higher latency, you would use like an M5 instance. Second, let's look at the advanced job that we have. The advanced job, you are flexible enough to provide the different types of parameters, like how long you want to run that job. Like your default job can run anywhere between let's say 60 minutes, but in your production you want to run it for 2 hours, right? In this case, I have set it for 2 hours. That's where I want to mimic my production traffic. I have the capability of doing that here, and I can choose a set of instances that I want to test against, which is not available on your default job. And you can also set the different parameters that you want to use for model tuning. OMP num threads is one of them. You might know that in Python, OpenMP uses OMP num threads to optimize your model and basically your model deployment. So you could use, and your model the threading, multi-threading. So you could use different values to test out your model capabilities as well. So we'll say how many number of tests that we want to run, how many parallel tests we want to run as well. So and also how many model invocations we want to run. So also, last but not the least, you can specify what is your P95 latency that you want to meet. Let's say in this case it was 500 milliseconds. So you can choose that as well. So if you look at the results of this particular job, you'll see if I need a lowest possible latency, I can start with higher instance count, and I can use a C5.x large instance to solve my problem. If I'm okay to tolerate higher latency, let's say here, I can start with lower number of instance and possibly use this OMP num thread value to this and visualize this. Yeah, so basically this brings us to an end of the demo. If you have any questions, feel free to reach out to us, and you can meet us outside, or this is our contact. We'll be happy to answer your questions. I hope you enjoyed the session. Thank you so much for coming in and attending in person. Thank you.